Okay, good afternoon, everyone. So today is the fourth interaction session. Am I audible? Savik, am I audible?
Yes,
Okay. So today is the fourth week of the interaction session of the course reliability-based structural design. So my name is Devashish Ponda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati. So I have been allocated to the course, and every Sunday from 3 p.m. to 5 p.m. we meet for the interaction session. And actually what we do during that 2 hours, so we solve tutorials related to the current week concepts or current week syllabus. So generally we first go through the concept of that particular week, then we solve the problems or tutorials which will be useful for your assignments as well as the uh, final exam. And then we solve the algorithm and problems using MATLAB. So today is the fourth week, and your fourth week, actually we will today discuss that Hasofer. First we will go through that Hasofer-Lind Reliability Index. Then we will see how to solve the first order reliability problems using Rackwitz algorithm. And if time permits, we will go through the Rackwitz-Fissler algorithm to solve some problem. Okay. So basically, during the last interaction session, what we have seen, we have, uh, we have solved problem using mean value first order second moment method, right? And we have seen some limitations of this method. So let's quickly revisit that mean value first order second moment method and Cornell's reliability index. So we derived that MVFOSM from, recall that from variance algebra and considering the Taylor series expansion, right? So here we just consider expand our limit state function using the Taylor series expansion, and we consider that our reference point is mean, and we can truncate the series up to the first order term. So for these two reasons, we have seen that our estimation of beta. So once we have found out the two moments using variance algebra, we can find out the reliability index, and whom we call the Cornell's reliability index, and that is nothing but the ratio of the first moment of the or first moment, we can say first moment of the limit state function at the origin divided by second central moment, right? And we have seen that using that mean value first order second moment method, we have some limitations, like we have seen that there is a lack of invariance problem. So we have solved problem regarding that lack of invariance problem. Like, what is that lack of invariance problem? If we change the limit state, like if we have the limit state g of x in the form of capacity minus demand, and if we change the limit state to that format, our problem will remain same, but we have seen that the final estimate of beta and pf will change. Like, we have solved the problem here, the solve the problem of cantilever beam, where first we solved that problem considering that gx equals to c minus d, and then we solve it again considering 1 minus d by c. And we have seen that using that concept of Cornell's reliability index and using the first mean value first order second moment method or MVFOSM, we have different betas and different probabilities of failure. Although the problem is same, but when we have changed the limit state, the final estimate of beta and probability of failure will change. And that is because of that two reason. Like, we have considered that mean point as a reference point for the Taylor series expansion, but this is not always the case that design point will be the mean point, and we have truncated the series at the first order term. Due to that cumulative error, we have some error that reflect in the form of that we call lack of invariance. Now, so what we have conclude last class, that we need some accurate method of solving reliability problem. So today we will see what another method or we can quantify that reliability index and how can we solve the probability of failure problems. So today we will discuss that Hasofer-Lind Reliability Index, and we will see how to solve the first order reliability method using Rackwitz algorithm. Okay, so what we have seen or what we have learned that first we need to define the limit state with respect to capacity and demand. So for example, we have a limit state in the form of capacity and demand. Okay, so this is our limit state, like c minus d equals to 0. So if we draw, it will give us a straight line on the original domain or original plane. So let's consider that our capacity and demand both follows normal distribution with capacity mean mu c and the standard deviation sigma c, and for the demand also that follows that mean value mu d and sigma d. Now if we transform this actual coordinate into standard normal space, so what will happen, just like we want to convert it into z domain here from x, from say let's say this was the x domain, actual x domain, and we want to convert it into z domain. So what do we need to do, you just need to subtract the mean from that capacity divided by your standard deviation of the capacity, will give the z1 and z2 d minus mu d by sigma d. Now we have c is equals to z1 sigma c plus mu c, and d is equals to nothing but z2 sigma d plus d. Now if we put that c and d in our original expression, what we will get, we will get the limit state in standard normal domain or standard normal space, we call it gz. So this is the limit state equation what we have started in actual domain x1 x2, and we have converted into a standard normal domain. So now that's that that straight line will shift here. So this is our new limit state g of z in standard normal space. Now in that space, how we can find out the beta? So beta, first we need to understand what is the definition for this Hasofer-Lind reliability index, and the definition says it is nothing but the shortest distance from the origin to the limit state function in the standard normal space. That means we need to find out this shortest distance from the origin. So we will get the beta. Once we will get beta, we can find out the probability of failure, and that beta is actually called the Hasofer-Lind reliability index. Okay, so here what we have done here, so we convert that limit state function into standard normal space, and now our task is to find that coordinate beta. So easily we can use that standard trigonometric form and we can find out that beta. And if we solve this problem, so we will see that beta comes out as nothing but your mu g by sigma g. That means the mean of the limit state function and standard deviation of the limit state function. But the way we calculate these two are different. First, like in MVFOSM, we have calculated that mu g and sigma g from the variance of algebra and considering Taylor series expansion, and our reference point was the mean point. But here we first convert the limit state into standard normal space, and then we find out the minimum distance of the you know limit state function in standard normal domain from the origin, and that definition of reliability index we call the Hasofer-Lind reliability index. And once we have found out beta, we can easily find out the pf is equals to nothing but phi of minus beta. Now for this case, we have seen that our limit state function is linear, right? So easily we can conclude that this is our design point. That means if we can find out that z1 and z2 value, and once we have found out that z1 z2 value, we can convert it into x domain. But the thing is, if we have a non-linear limit state function. So first let's uh, that summarize this thing up to this what we have done in Hasofer-Lind reliability index. So first what we do, first we take a limit state function in actual domain, that means x or x1 x2 domain, then we convert it into gz domain, that means standard normal space. And to convert the standard normal space, like we just need to subtract the mean and from that particular variable, and then we divide it into our standard deviation of the particular form, and we need to find out the minimum distance of that limit state function from the origin. So we'll get the design point and beta. Once we get z1 z2, we can convert it back to that x1 x2 original domain. Like, it's the reverse process. Now if we have like non-linear limit state function here, the first problem was we have a linear limit state function, so we can easily find out the point using the using the tool of trigonometry. Now, if we have a non-linear function, how we can find out the optimum point or MPPs, the most probable points? So, how we can find out? Like, every points on this limit state, like here, that gz is a non-linear function. Okay. Now we need to find it out. What should be the minimum distance from the origin? So we can find out beta, and corresponding values of that point will give us the design point in the standard normal domain. So it's nothing but we need to optimize our, you know, limit state function to find out the minimum value of z. So it's nothing but an optimization problem, and for this optimization, during the course, the Lagrange multiplier technique has been used. So you all know about the Lagrange multiplier technique. So first you need to formulate the Lagrangian function with respect to that constant condition, whatever you have given, and then you will find out that sort of equation n and one equation for this constant condition. So here the constant condition is like your all points should satisfy that gz equals to 0. That means you need to consider the points which will lie only on this limit state function. That points cannot be, you know, beyond that function. So it's nothing but an optimization problem, and for this optimization problem we use that Lagrange multiplier technique to get the optimal solutions. So first we need to define the Lagrangian function. First, Lagrangian function define that g(n). That means we need to optimize that z points in standard normal domain. Now we need to set the Lagrangian. So Lagrangian is nothing but your optimization function plus lambda. This is nothing but your Lagrange multiplier, and this is gz. This is the constant condition. So here we have only one constant condition, that all points should lie within that g star value, right? That means within that curve. Now, recall that Lagrange multiplier technique. What we need to do, that first we need to differentiate that Lagrangian function with respect to the unknown variables, and we need to equate to 0. And also for the constant condition, we need to differentiate the Lagrangian function with respect to the Lagrange multiplier, which will ultimately give you the constraint conditions. So now if we solve this and look for the optimal solution, so what we will get, that optimal solution for z is nothing but comes as in the term of lambda, dn and g star, and dn is nothing but your Euclidean norm of z. So by this way, if we solve the problem, we will find out that beta comes as nothing but minus z star g transpose by Euclidean norm of g. Now I will explain all the terms one by one in a minute. Just hold for a second. So we have found out the optimal solution if we use that Lagrange multiplier technique to minimize our problem. So the final solution of this is found in the term of this beta is equals to nothing but z star g star transpose by Euclidean norm of g. Now what is that g? Refer here. G is the gradient vector of the limit state function in standard normal space. That means that vector will consider like dg by dz1, dg by dz2 and all this. Okay. And Euclidean norm of z is nothing but norm. So under root of square square square, you just added them. So the final solution is beta is nothing but z star. That means the design point on the standard normal space on nonlinear limit state function. Now further we can write it down like this, that alpha I in the terms of direction cosines. These are the direction cosines. So alpha I we can write it down. It's nothing but minus the that norm of or the gradient of the limit state function in the standard normal domain divided by Euclidean norm. So if we can define alpha in terms of gradients of the limit state function in standard normal domain, so we can find out this. So our final solution at design point z star will be equals to alpha I into beta. This is an very useful information while we solve first order reliability methods using Rackwitz algorithm. Now, once we have that z star values and we found the beta value, we can convert that z star into x domain. Like when we have considered that z1 is nothing but x1 minus mu x by sigma x. So once we have z1, we can find out the x1. x1 is equals to nothing but z1 into sigma x plus mu x. That means we will get the design point in our actual domain. So let's summarize this process. Then we will solve problem. Then everything will get clear how we can process this. So that means here in Hasofer-Lind Reliability Index, we just convert the limit state into standard normal space. Then we look for the MPPs, that means most probable points, or we can say the points which will give us the shortest distance from the origin to that limit state function. Okay. So if we summarize this algorithm, and this algorithm as a whole called the Rackwitz algorithm to solve the first order reliability problems. So first, what we need to do, let's quickly recapitulate or quickly go through that algorithm. So what today we will do, we code this algorithm to solve first order reliability problem in MATLAB, and also we will solve problems like pen and paper, 2 or 3 iteration we will solve. Then we will directly go to MATLAB and we will code that algorithm and solve different kind of problems. So first we need to understand this algorithm, how this algorithm works and what is the flow for this algorithm. So first what we need to do, first we need to define the limit state function in gx, that means that actual domain. Then we need to convert this limit state function into z domain. How we can convert it? We know that z is equals to nothing but say z1 x1 minus mu x. You will need to subtract the mean and divide with standard deviation. That means standard normal space, we just convert it into standard normal space first. Now first thing we have done. Now what we need to do, we have seen that we need that gradients and direction cosines of the limit state function. So we need to evaluate the derivatives of the transform limit state. That means the limit state we got from the standard normal space. Okay, once we got the derivatives, so first what we need to do, first we need to define some initial value of beta and some initial value of alphas, direction cosines, like alpha 2, alpha 3 and all this. So how? Like initial value, why we need to define initial values? Like if we see here the optimization problem, it starts for a minimal MPPs based on the initial value whatever you have provided. That means the algorithm start from that point, then it start iterating until the convergence is achieved. And the convergence criteria we set like how much tolerance we will give between two successive betas. Okay. Now, once we have that, so we can evaluate that expression of limit state into gz, and we know that in z domain at design points that z star equals to alpha I into beta. So we can formulate a formula with respect to alpha I and beta on the standard normal domain, and we can solve for beta, right? Now once we get the new beta, again we need to calculate the direction cosines and check for the new beta, and we need to repeat from step 4 to step 8 until that beta final minus beta fi, that means two iterations, say I plus 1 and I, that should be well within the tolerance. Say for example we have put the tolerance as 0.001. So until that the difference between that two successive betas we will get, we cannot achieve the convergence. And until when we achieve the convergence, or we can calculate the beta, we can calculate the zi points. Zi is nothing but alpha I into beta. What is that alpha I? The direction cosines related to your that variables you have provided. Now once we have zi, now we can convert it into again the original space. That means we can get the xi. So we have started from the actual domain, we convert it into Z domain. First, we take some initial values of alpha and beta. Then, based on that alpha and beta, we calculate new beta. Based on new beta, again we calculate alphas. And based on that alpha and old beta, we calculate new beta. And this iteration will continue until the convergence will achieve. And once the convergence will achieve, that means one, we can find out the final beta and corresponding direction cosines. For that beta, we can find out the Z points. And what will be the Z points? That will be the design points on the standard normal domain. And when we have found out that Z points on standard normal domain, we can directly convert it back into X domain to get the design point in our actual domain. So this method of solving the first order reliability problems we call the Rackwitz algorithm, and the reliability index we call the Hasofer-Lind Reliability Index. That means in Hasofer-Lind Reliability Index, what we need to do, you just need to convert the limit state into standard normal space and look for the minimal distance point from the origin to that limit state function. So here for the nonlinear case, that is achieved through the Lagrange multiplier technique. That means we need to do some optimization to get the most probable points, and once we get the most probable points, we can convert them back into the original space. Okay, so until we solve one problem, this thing will not get clear, right? So let's solve one problem first on pen and paper, then we will solve some problem in MATLAB. So till now, Abdul, let's solve one problem, right? Do you have any queries? Like until we
No,
solve one
not
problem, yeah, don't clear ourselves. So first let's solve one problem and be focused, and please you also solve one by one. First we will solve one problem like 2 3 iterations on pen and paper, then we will go for MATLAB and do that algorithm on that MATLAB. Okay, so first we will do one problem on pen and paper. So here one more thing I can highlight, that the random variable what we have considered for our gx, that can be uncorrelated normal, uncorrelated normal, correlated normal, and correlated normal. For 4 cases we can see, like correlation may be there, correlation may not be there. The random variables can be the normal random variable, all the random variable. Like if we have a gx like that, say x1 x2 minus x3, so that all random variable can be normal. So that can be a case, normal and uncorrelated. That means no correlation was there. One case will be there, like one of the variable can be non-normal, so we need to convert it into normal first, then do the solve or do problem. One case may be that normal and correlation will be there, so correlation first we need to uncorrelate that things, then we can solve the problem. And one case where the correlated or correlation will be there and the variables will be non-normal. So we will see all these problems one by one and we will solve, that will get clear. So first, like this problem I have solved like pen and paper, and this problem is taken from the Ranganathan book, R Ranganathan. Okay, so let's solve this problem by hand. Then we will go to solve different kind of problems using MATLAB, and also pen and paper also, which will be required for your assignments. So look here, what is that problem says? Is it visible? Like I just write it in a copy. So bear with it, and I will upload this thing. No problem. Okay. Okay, so Abdul and Robert, both you should focus like this, how we can solve this problem or problem within using that Rackwitz algorithm. So first, let's read the problem. Determine the reliability index of a simply supported I beam at the limit state of shear. Okay. Now here the random variables are given, like Q, the shear force, Fs is given, and D is given, right? And all are normal and uncorrelated. And some values are also provided here, like for the depth, sigma d is given, like depth to wave thickness ratio is also given, and this you can already figure it out. So we just need to look for the limit state function, and the limit state function is already given to you, like the limit state function is given with respect to shear, already that is provided, and that says this is nothing but fs multiplied by twd minus q by 2. This is your limit state function. So you can take like fs is equals to x1 and d is equals to x2, because look, our random variables are shear force, fs, and depth d. So three are the random variable here. So we have in our limit state, we have three random variables, x1, x2, and x3. So here I haven't put that x1, x2, x3 thing. I just directly go with that fs, tw, and q, whatever the random variables are provided. So we have three random variables, fs, d, and q. Like here, all the parameters for these three random variables are given and they follows the normal distribution. So what should be the first step? We need to convert the limit state into standard normal space, right? So this is our limit state function, g of x is equals to fs multiplied by tw multiplied by d minus q by 2 is equals to 0. This is our first equation. Now, we need to convert it into standard normal space. So what we need to do, say Z1 is equals to nothing but what we have seen, x1 minus mu x1 by sigma x1. So here the random variable is fs. So fs minus mu fs by sigma fs, right? So we can find out the value of fs is equals to Z1 into sigma fs plus mu fs. Likewise, for the other two random variable, we convert it and get the values of the variables with respect to standard normal space. Now put those values of fs, d, and q in equation number 1. So what will you get? Put it. You will get the limit state function in standard normal space. So let's quickly put it and simplify this equation. So here I have put it all the equation like TW into the value. Here the value was like Fs, and Fs is nothing but Z1 plus sigma Fs plus mu Fs, and likewise D, for the D value I have put this, and for Q value I have put this. So up to this clear? So we take the limit state function in actual domain, we convert it into standard normal domain, and we have the limit state equation in the standard normal domain. If we simplify it, we have the limit state function in standard normal space. Clear up to this? No problem? Yes or no?
Yeah, it's clear.
Okay. Now we have, once we have the limit state function in standard normal space, what we need to find out? We need to find out the direction cosines alphas. So to get the alphas, what we need to do? First, we need to differentiate this limit state function with respect to the unknown variable. So here the unknown variables are like Z1, Z2, and Z3. Three are unknown variables are there, like Fs, Q, and D. So let's make the derivations. So here, yeah. So first, with respect to Z1, if we differentiate that function, we will get 625 plus 31.25 Z2. Likewise, with respect to Z2, if we differentiate, we will get this. And if we differentiate with Z3, we will only get minus 500. That was the limit state function. You can easily differentiate with respect to Z. Here, you have all these values. So you can easily differentiate with respect to Z1, Z2, and Z3. Okay. Now, once we got that, these are nothing but our gradients of the limit state function, right? Gradients of the limit state function. Now, once we have gradients, we know the expression for alpha. What that alpha says? Minus of gradient of the limit state function divided by Euclidean norm of the limit state function. Yes or no? We have that formula. So, like say, let's say the Euclidean norm of the limit state function, let's consider this as a k. For now, let's consider as a k. So what will be the alpha 1 value? So alpha 1 will be nothing but minus 1 by k, the first derivative of the limit state function with first variable. Yes or no? That's all. Now Sigma 2, how can we find it out? Similar way, minus of dg1 by dz2. And sigma 3 is that. So these are the direction cosines which we can derive from the derivatives of the or the gradient of the limit state function. Now look, first we don't know, we don't have any direction cosines, so we need to start from initial guess of the direction cosine and initial gate of beta, because look at the expression of this z1 z2 and z3 and design points. What we know, z1 is equals to alpha times beta, yes or no? So let's consider the equal weightage of the direction cosines. So what is the property of the direction cosine? We know the square root of the direction cosines always give you 1. So tell me here, how much random variables are there? 3 random variables are there. How much direction cosines we will get? We will get 1, 2 and 3 direction cosines. So initially we will provide that equal weightage of direction cosines. Okay, equal weightage of direction cosines. So if we provide that equal weightage of direction cosine, that means 1 by root 3 we will get 0.58. So you can provide like alpha 1, alpha 2 and alpha 3 is equals to, you can start with directly 0.58, 0.58 and 0.58 equal weightage. Here what I have done here, like to skip some iteration, I have directly pointed out the direction of the direction cosine. Like how we can see that, or how we can conclude that, we know that alpha direction cosine is nothing but minus of 1 by k, that is the Euclidean norm of g, and dg by dz1. That means one minus sign is there. Now look for these derivations. Here there is no minus sign, so obviously I put that okay to be the uniform direction. Let's consider this minus and alpha 3 as plus, because look at this here expression, already minus is sitting there. So obviously if we put plus there, ultimately we will get alpha 3 as a form of minus 1 by k dg by dz3. Clear? Okay, so these are the
Is that the normal trick?
yeah, yeah,
Is
Bob.
that the normal trick?
What? I
Is that the normal trick? Trick.
didn't get tell a response.
Okay, I'll type it.
Actually, I didn't get what you say. Just like can you repeat it once?
What I'm saying that is that the normal trick?
Okay, no, there is not like that. You can start with 0.58, and 58. Like you just need to do one iteration to get the next point, just like that. We will see that if we start with that plus one and plus one, we will get the same value like this. We will solve another problem regarding that also. Okay.
Okay,
Okay.
thank
So
you.
like initially we need to get some value to start with that. Like if we see that thing here, just visualize that thing. Like when, like here we just have this limit state function. So first the algorithm will start where you want to define the points. So like if you want to define the points here, so it will start from here, then it will calculate here or here and here, then it will ultimately converge here. So the initially you need to provide some values. We will see when we will solve during MATLAB that if we increase the values of beta, so it's nothing but it will take some more iteration to converge. Okay, so like for this problem, what I have done, like I have fixed the direction initially so that my first iteration will skip. Okay, that's all, nothing but. Here you can also take 0.585858, so you just need to do two more iterations. So we will see in a minute, like one more problem. So we take initial beta and initial alpha. Now once we have that alphas and betas, now we can calculate the value of the new alphas. How? So we know what we know, that Zi is equals to alpha I into beta. Now put here instead of Z, alpha into beta term. Instead of Z1, alpha into beta term. We can do it, right? So now if we put that thing, so we will get the new value of beta. How? We will see. So at a design point, what we know that Zi is equals to beta into alpha I. We just have seen in a minute that the design points are nothing but equals to beta times alpha I. Now we have that Gz in terms of Z1. Like we have this equation. Fine, we have convert this limit state function Gz. Now what you need to do in that equation, instead of Z, what will you need to put? What you need to put instead of Z? Alpha 1 into beta. That beta, actually we need to first assume that beta where you need to start the iteration. So we consider the 3 as the initial beta. We have considered, like here we have considered the initial beta and initial alpha, like here the initial alpha and initial beta. We have start from 3. Okay, that is the initial beta, initial guess of beta.
Okay.
Okay, so you can
All
start
right.
from 2
Thank
or
you.
3, but 3, why we take 3? If if you calculate the probability of failure corresponding to beta 3, that most of the engineering structures will fall within that range. That means we need to do less iteration to solve the problem. Okay.
Okay.
Okay, so once we put that z equals to beta into alpha I, we get the limit state function in the terms of beta and alpha, right? Yes or no?
Yes.
Now put all the value of alpha and initial beta. Like alpha I, we have considered that alpha I is equals to minus 0.58. I have put here. Now again alpha 2 minus 0.58 and alpha 3, that is 0.58, and beta we have considered the beta as 3. Yeah, the beta is 3 because in that equation the beta will sit. That's why you need to consider an initial beta. Now if you solve for beta, you will get that beta is equals to 4.96. So we have started here beta is equals to 3 and some alpha value giving same weight is 0.58, 0.58, 0.58. And from this 2, we put that limit state function on the standard normal domain, we will get new beta. Clear up to this? We will get new beta. Now once we get the new beta, we need to find out the new alphas corresponding to that new beta. How we can find it out? Again, use that equation and use the properties of the direction cosine, right? So we have the derivations here. Use the derivations of the limit state function, or in standard normal domain gz by g del g by del z1, del g by del z2, and del g by del z3. So we have a new beta 4.96. So alpha we can write out, alpha is equals to nothing but 1 by k. This is the first derivative. Here we already have here first derivatives of these things. 625 plus 31.2 alpha 2 into beta. Just put that values here. So you will get alpha 1 is equals to this, alpha 2 is equals to this, and alpha 3 is equals to this. Clear up to this? Yes or no? Tell me. If you have any doubt, yeah, ask me. Otherwise, we will not understand how we are going to code it.
Okay. It's fine.
First, what we have done, just quickly go through it again. First, we have write down the limit state function in normal space. We convert it into standard normal space. That means in Z terms. So we have this equation. Once we have this equation, we have the derivatives of the limit state function with respect to Z. And we know one more thing, that at design point, Zi equals to the direction cosine into beta. So we have this equation, all this equation in the term of alpha and beta. Clear? So to solve the beta, we need to consider an initial beta and initial alpha. So we consider some initial value of alpha and some initial value of beta, the starting point. Okay. Then using that beta and alpha, if we solve this here, put this equation, we found out the new alphas. Yes or no? So precisely we have done this. So here we have the new alphas. Now we know the properties of alpha, that alpha 1 square plus alpha 2 square plus alpha 3 square is equals to 1. Now put these values, you will find the value of k. So here I have solved this problem here, like just put it here. So you will find the k value. Once you find the k value, you will find the alpha 1 is equals to minus 1 by k, your dgz by dz1, alpha 2 is equals to minus 1 by k dgz by dz2, and alpha 3 is equals to 1 by k, your dgz by dz3, right? So you will get the new set of alphas corresponding to beta. We have found out that 4.96. Clear? So initially we have started from 3, then we have reached to 4.96. Now again we need to calculate new beta based on these alphas. How you can calculate it? Again go back to your equation in standard normal space and put these values. Right here the equation of beta, so you have beta is equals to this, and you have new direction cosines here. Now put these values in the equation. What is that equation? What is that equation, Bob? What is that equation? This is nothing but the equation of limit state function in standard normal space. Yes or no? That equation 3, we are
Yes. Yeah.
dealing with this equation. It's an iterative
Yeah.
process. The iterations actually we
Yeah.
are doing here. So again, we
Yeah.
found out the new beta, and that comes as 4.67. So once we have new beta, we can again solve it for alphas. Similar way, go back to your direction cosines, find out the direction cosines, give the directions, get the new beta. Now, until we have that beta 2 minus beta 1 is equals to some error, say 0.001 or 0.002, whatever you have set the limit, until then this algorithm will work. Clear? So again, you have beta, you can find out the alphas, new alphas. Yes or no? Can you?
Yes.
How?
Yes. You can find it.
Yeah, how? You have beta, you have alphas. Go back to your that formula dz, the direction cosines dz1. You have that formula where beta and zi are there. Put there, you will find alpha 1, alpha 2, and alpha 3. And once you have alpha 1, alpha 2, alpha 3, and you have one beta, you just go to your equation, whatever you equation you have, like this equation. Again and again we will use this equation, and we have seen that our beta on the third iteration comes as 4.7. Okay, so let's stop here. Like, okay, we have conclude like 4.7 is our convergence. Now once we have beta as 4.1 and the corresponding direction cosines like this, can we find out the z1, z2, and z3 value? Can we, Abdul? Can we? This is beta. Let's say we have achieved the convergence in 4.7. Can we find what is that z1, z2, z3? These are the
Yeah.
design points. Design points. Now how we can find out the design points? How we can,
Alpha.
alpha 1 into beta, alpha 2 into beta, alpha 3 into beta. Now once we have that z1 and z2 and z3, can we get the x1 and x2 x3 back? Yes, just convert it into the actual domain. So we will get the final form of beta. So if we see in a tabular form, here I have provided. So we have started with that value. Then in first iteration, we have found out 4.97. Second iteration, we have found out 4.27. And in the third iteration, we have found out beta as 4.7. So here, like I have put that tolerance, like you just minus it 0.003 something. So it may be like we will solve, when we will solve problem using MATLAB, we can set the tolerance as 0.001 or 0.002. So number of iteration will increase. So this is your final beta is equals to 4.7. Now once you have found out the beta, you can find out the probability of failure, phi of minus beta. And once you have beta, you can find out the z1, z2, and z3, and corresponding you can convert it to x1, x2, x3. That means you will get the design points at actual domain or in actual space, we can say. So what, now let's quickly summarize the algorithm, then we will solve one problem so that our concept will get clear. So actually these problems cannot we can solve using pen and paper all the iterations. So, like you have seen, like 3 and 4 iteration, you need to calculate it again and again until the convergence achieved. So we need to code it. But still, here I have added how you can solve one problem using pen and paper. You can solve it if you have patience, and if you can, or the numerical calculations, if you are doing rightly, then you can have the same level of convergence. So let's quickly revisit our algorithm so that this thing get clear, more clear. How this principle applied in a normal design process. Normal design process, like, yeah, we will see in a minute. Normal design process, like if we have a limit state, we will see like normal design process, we just solve this problem. Normal design process, wait, just I will tell you, like whatever the problem we have solved here, look at the problem. This is the problem of a I beam, like where the shear stress, shear force, depth and fs, three are random variable. Now, if you need to find out the design points, how you can find it out? How we have solved the design points here? We have solved using Rackwitz algorithm. So we can find out the final design points and final reliability index. It is applicable to our design points. Yes or no, Bob? In your design
Yes, we
problem,
can do that.
yeah, if you have the limit state, we can solve the reliability problem and get the new design points, right? So this is the
Yeah.
application.
Yes.
Like if we solve another problem here, we will solve another problem again. So
Okay.
like here,
Okay.
this is the problem. Like we have a cantilever beam and one point load is acting on the free end. One point load is acting on the free end, right? So we have a limit state function in the term of x1, x2 and x3. So now if our fy, z and l are the random variables, or p are the random variables, what should be the design points? What should be the most probable design points? How we can find it out? You just solve this problem using Rackwitz algorithm, find the optimum beta, find the z star points and find the x star points. These x star points are your design points. Clear?
Yes.
Yeah, like we will see for this problem, like see this problem, like for this we have a cantilever beam and one point load is acting on the free end. Now our limit state is defined as x1 x2 minus x3 l, where x1 x2 and x3 are the random variable. Now look, first the mean of the random variable are given as 2.5 into 10 to the power 5, 1.2 and 100. These are the mean and standard deviation. Can we consider this as a design point, Robert? No, because these are random, we cannot take them. So finally
Yeah.
we need to find out some design points based on which we can proceed our design procedure, and which the points will be more probable points. So we can find it out through MBFOSM, but in MBFOSM what we have seen that there was lack of invariance problem. So we can use the Rackwitz algorithm to find out these optimum design points. Now let's solve this problem, then we will further move. Then I think this will get clear. So first step, what was the first step of Rackwitz algorithm? First, write down the limit state function in x domain. So our limit state function in x domain is nothing but x1, x2 minus x3l. Clear? Is equals to 0. Now what we need to do? We need to convert into standard normal domain. So to convergence, we have this. So Z1 is equals to nothing but x1 minus mu1 divided by sigma 1. Similarly, rest. So put this all values. So x1 is equals to, we found out, mu1 plus Z1 sigma 1. Just put it here. Instead of x1, I have put here this for the x2 here and for the x3 here. Up to this clear? Now simplify the equation. You will find out this as a limit state function in standard normal space. Now, what do we know? at design points, Zi equals to nothing but your alpha I into beta. That means Z1 is equals to, we can write alpha 1 into beta. So we can further simplify this equation in term of this alpha and beta. Clear? Z1, you just put alpha 1 into beta. Z2 similarly alpha 2 into beta. So we can simplify it up to this. Clear? Now what we need to do? We need to find out.
Please, where's
Yeah,
the 1.5? Where's the 1.5 coming from?
yeah,
The 1.5, the first figure, 1.5 alpha 1, alpha 2.
1.5.
Yes.
1.5 what?
The function GZ. If you consider GZ,
Yeah,
after the substitution,
yeah.
I'm seeing some 1.5.
1.5. What 1.5? I just didn't. This 1.5.
Yes.
Okay, this 1.5 is like substitute the. I think I have substitute the value of Z here, mu Z and sigma Z value. You just simplify this, put this like mu 1. You have the value of mu 1 here. You have the value of sigma 1 here. So just I have simplify the equation and I just get it.
Okay. Okay.
Just
All right. Okay.
mu and sigma. Just put the value of mu and sigma. Z1 is equals to
And
alpha
simplify.
into beta. So you have the mu and sigma 1 value, mu and sigma 2 values. So just put it. Okay.
Okay. All
And
right.
after simplifying, you will get this equation. Here, look that sigma, mean and standard deviation values are just put it and simplified it. Okay. So now what we need to do? We need to find out the gradients of this. That means we need to differentiate the gz function with respect to z1, z2, z3. So we will find out this. Clear? Now what we need to do? We need to consider initial value of alpha. So here we have three random variables. So we can have that alpha 1 plus alpha 2 plus alpha 3. If we put equal weightage, under root of square is equals to 1. So let's say we will provide the equal weightage of alpha. We can do it. Okay. Now initial beta I have considered at 3. Now when we have alpha and beta, I can consider the z star. What is that z star? This is nothing but in a matrix notation. So it is nothing but z1, z2, z3. So alpha 1 times beta, alpha 2 times beta, alpha 3 times beta. So these are the initial z values. Clear? Now what should be the gradient of z? That gradient of z, that consider nothing but your dgz by dz1, dgz by dz2 and dgz by dz3. Now if you solve them, you will get the matrix form. Just put this value 1.7 into here, here, or here. Or directly you can consider here z2 equals to alpha 2 into beta. Whatever you want to do. Like in the first problem, I have first simplify the equation and then put the corresponding values in the equation. Clear? So these are the initial alpha. This is initial beta. That is initial value of z. This is the initial value of the gradient vector of z. Now, once we have these all values, we can find out the alpha in a matrix notation. It's nothing but minus gradient of dz. That means dg by dz divided by Euclidean norm of your z. Now, solve it. You will get the alphas. Now, quickly solve it. Quickly solve it. And tell me if you are getting the alpha values like this or not. So, first, alpha 1. What will be the value of alpha 1? What will be the value of alpha 1? Bolo, bolo. What will be the value of alpha 1?
32.5981 divided by the given gradient. Sorry,
Yeah.
not
Norm of that. Norm of that means under root of this square plus this square plus this square. 32.59 square plus 17.59 square plus 30 square. Now calculate it in and check whether you are getting this value or not. Now why I am focusing on that? Because the directions. Just check it, Abdul.
0.6838.
Yeah, and what is the sign?
Negative, minus.
Yeah, minus, right. Now only for this thing, that alpha 3 we have the positive value, because already here negative is sitting here. So negative negative will get positive, so obviously the final value should be positive. So we will get that alpha is equals to minus this form, in this form, minus like del g by del z by norm of your z form. Clear? So these are the initial alphas based on what we have provided for the first iteration. Now what we need to do? One, we have alpha 1, alpha 2 and alpha 3. Can we calculate beta? From where we can calculate beta? Bolo, from where we can calculate beta? From this equation or not? Yes, or I have already simplified the equation here. Clear? Now put the value of alpha, alpha and initial beta. Can we get the value of beta from this equation? Yes or no?
Yes, we can get beta.
Yes, we can find out beta. Like alpha 2, alpha 1. I know beta is equals to 3. Now I can solve for new beta. And tell me, what is the beta value? Just calculate it and tell me. Just calculate it. Otherwise, that thing will not get clear. So we have found out this. Now in this equation, what you need to do, you need to subtract z equals to alpha 1 into beta. And what I have already solved in the form of alpha and beta here, whatever you are asking for, this equation. So you just need to solve this equation. Now if we solve this equation, what we will find? Like it's a quadratic equation, we will get, like put the value of z here, you will get a quadratic equation of beta. Yes or no? Because look at here, z1 and z2 term is sitting over this value. So obviously you will get beta squared term here. Yeah, like this beta squared term. So you will get a new beta, and that is 2.26. Now once you have found out this beta, what you need to do? Again, based on this beta and based on the direction, based on the gradients, you need to find out the new alphas. Clear? And based on the new alpha, you again find out the new beta until the convergence achieve. Like here in the tabular form, I have given that stop criteria is beta k plus 1 minus beta k should be within the tolerance limit. And I have set the tolerance limit as 0.001. So I have seen that after third iteration, it will get converged. So see, in the first iteration, we have started with 3. We have considered equal weightage of the direction cosines. Just be with me. Direction cosines. Then what we have found out, based on these two, we have found out new beta and new direction cosines. Once we have new direction cosines, based on the new direction cosine, we again find out the new beta, and from the new beta, we have found out the new direction cosines. So we have seen that between iteration 2 and 3, that stopping criteria is achieved. That means the convergence is achieved. Okay. So this is our final beta. This is final alphas. So once we have alpha and beta, we can easily calculate what is the final design points. These are the Z stars. And once we have Z star, we can convert it back into X star points. So how? So these are the final design points. Now check the problem. What was the mean values for this? What was the mean values for this? 2.5 into 10 to the power 5, 1.2 10 to the power 3 and 100. Now what we are getting here for the most probable points are 2.12, 1.16 and 123. Actually, these are your design points x1, x2 and x3. While you will design your structure considering the randomness for these three variable, and for this beta, beta is equals to 2.2577, and corresponding probability of failure is nothing but phi of minus beta. From the standard normal table you will get that. So to achieve the beta of this and probability of failure this, your design point should be this, to 2.12, 1.1 and 126. Instead of what we are starting from, we are starting from here, initial guesses. So by this way, this method is applicable to our real life problems where we need to consider the reliability, the randomness in our limit state function. Clear? Yes or no?
Yeah.
Yeah, but you need to solve it by your hand, at least one problem. Otherwise, these things will not get clear. So we will code in a minute and we will see step by step how we can solve it. So is the algorithm is clear how we can solve the problem? Tell me. If there is any doubt, ask me or we will move forward. Is there any doubt how we have started here and how we have concluded? So let's revisit the algorithm once again. So this handwritten problem is important. Just go through it like step by step. I have added. Just you just need to give some time to solve it. I will upload it, no problem. Okay. So let's revisit the algorithm. First, what we need to do? We need to transform the limit state function into Z domain. And this gz, actually based on this limit state function, we are doing all the calculations. We are all the calculations is nothing but if we visualize these things like here, if we want to visualize it, like say initial beta I have provided here. So based on that beta, and here we have some z1 z2 and z3. For this z1 and z2 and z3 we have some direction cosine, so it will start from here, then it will go to next point, then it will go to next point, then it will go to next point until the stopping criteria is achieved. That means it will find out the point based on your direction cosines, and direction cosines are defined based on your gradient vectors of the standard normal space, the limit state function in the standard normal space. Clear? So this is the algorithm. First, we need to convert it into standard normal space. We need to evaluate the derivatives of the transform function in standard normal space to get the direction cosines. Then we find out, first assume initial value of beta and initial value of alpha. Then based on initial value of alpha and beta, we can calculate the beta value from that gz, because we know that in design points z is nothing but alpha times beta. Now once we solve the beta, new beta, we can find out the new alphas. Again we find out the new betas, and this iteration process will last until the convergence is achieved. And convergence criteria is like for two iterative betas you can set some convergence criteria. So this method of solving, or this algorithm of solving the first order reliability method, is known as Rackwitz algorithm. Clear? So like we have I have different kind of problems, but I need you to solve one problem that only that can help. Yeah, Robert, you want to say something?
No, no, it's okay.
Okay. So like here we will see that this invariance, lack of invariance problem will also be addressed using this. I will be in a minute, but still let's solve some very easy problems. Okay, so let's solve some easy problems so that these things get more clear. So like here we have a failure surface in standard normal space is given, gz is given. Okay, like zz equals to 625 z1. Just put your calculator and just calculate it. Z1 312 z2 and 31.25 z1 z2 minus something, this is your gz is given. Now the question says taking initial beta is 6. Look, you can consider any beta like 6, 7, 8, 9, 10. Just need to do some more iterations, just like that. Now the direction cosines, the value of direction cosines are given. Alpha 1 and alpha 2 is minus 0.58 and alpha 3 is equals to 0.58. Equal weightage with some directions. Now calculate the value of reliability index beta for the first iteration. How we can calculate it? So first, this is your limit state function in standard normal space, Gz. Clear? We know at design points z I is equals to beta times alpha I. So put these values instead of Z1, beta times alpha 1, instead of Z2, beta times alpha 2, instead of like here Z1, Z2 will be there. So beta square alpha 1, alpha 2. Again, we have beta alpha 3 and 400. Now, if we want to solve for beta, so just take the beta from left hand side, you will get this formula, right? Previously, just we have solved it. Now look, to solve beta, we need initial alphas and one initial beta 2. And the values are already provided. What are the values? Alpha 1, alpha 2 is equals to that, alpha 3 is equals to that, and initial value is this. Now put all these values and calculate the beta and check whether the value is coming as 5.19 or not. Are you getting the value as 5.19? Calculate it, just calculate it. How this process have solved. Are you calculating it, or we can move to next problem, or just solve another problem? Now I think the process and the
Excuse me. Yeah,
yeah.
sorry. Actually, this method that you've used over here, is it not different from the given steps that we had? I mean, this is a very good method, direct method, where
What
you have
happened?
taken. I mean, look at, if you look at step number three, where beta is equivalent to minus 4,000 divided by the whole thing,
Yeah,
and you have beta over there as well,
yeah,
and then you've just substituted 6 into it, and you've got the value, right?
yeah, yeah,
But given the steps that we already had,
yeah.
fine, that would have been a bit longer, na? We would have basically, we were supposed to get the roots of a quadratic equation in that case, if we
Yeah,
follow the
but
brief.
not the roots. Roots subjected to a constraint that you all the points should lie within the limit state. That means you need to find out the roots in iterative way so that the final root will converge. That's the
Oh,
process.
okay.
And here I have started from 6. That's why. You need to converge the beta. Cannot take the initial beta and initial alphas. You need to final beta with corresponding to the minimum distance. So it will find out, like this algorithm is trying to find out which point should be the minimum point, and that's all. And this finding root findings are based on the direction cosines. Okay.
Um,
Okay.
yeah. You see, when you made beta the subject,
Yeah.
there's another beta under the 4,000. Now I see the same beta, but you just factorize one beta out and left the other. So I have a little bit doubt there.
Like it's an iterative process. You need to like how you can solve this equation. Look at this equation.
Okay.
How you can
Yeah.
solve this equation. So if you solve this how you can here beta and beta, so you will get the root of beta, but that beta is not the optimized beta for you. You need to find out some beta that will give you the minimum distances, that means mpps. That means you need to find it out. Here that initial beta is starting with that 6. That might not be the case,
Yes.
that your probability of failure will corresponding to beta is equals to 6. You need to find out the minimum value of beta. That means the minimum distance point corresponding to that beta. Got it? So here for
Okay.
the
All
first
right.
iteration they have said the to first iteration you need to solve it, but that may not be the case until you need to calculate it, until you get the convergence. Like just just try to visualize this point, why these iterations are occurring or happening. Like for example, like for here, if like I'm saying that beta, I don't know what should be the most probable point here. I don't know here, like Most probable point will be here. I just have a limit state. Here the limit state is like a parabola. It might be like limit state might be different type like this limit state. Okay. How we can find out the most
Yeah.
probable point? What should be the most probable point? So you need to start from a point, then you need to find out the minimum distance point, and this algorithm precisely doing that based on the direction cosines. So first, like if I provide a value here, so first value of beta it will take this, then that will calculate the another beta based on this, and it will look for the beta until your convergence will achieve. Get it? This is not like that from first
Okay.
iteration you will get the convergence. It may be you need to go up to 10 or 12 iteration to get the convergence. Okay.
All right.
It's finding out
Thank
the
you.
optimal points based on the direction cosines. Get my point? It's like MPP search. It is searching for the MPPs based on some initial values you are provided. Start to karna hoga kaise. You need to start from somewhere. So just put some initial values and start the algorithm. That's all. Okay.
Okay.
Okay. And MVFOSM, we will directly getting the value, but that value should not be the case that we will get that design point from there. Okay. Great. And this problem just we have solved here, like let me go to the problem first, then I will discuss it. Here, this problem. Look, this problem. Like we have started from a beta 3, but our convergence is achieved at beta is equals to 2.25. So if we stop here 3, that means our design point, the estimation of the design point will give us the wrong estimation. Yes or no? Definitely, that will
Yes.
give us the wrong estimation. So our goal is to optimize that beta so that we will get the most probable points. That means we need to find out the minimum value of beta. Clear? That is our main goal. We don't know where on that limit state surface from where we get the minimum value. So we start from somewhere, some points. Like here we always start from 3 so that we can achieve the convergence easily. That means most of the engineering structures have reliability with corresponding to beta is equals to 3 plus minus 1. Okay, most of the engineering structures. That's why we started from 3. Okay, now clear, or is there any doubt? Like here, look at this problem. It's a it says like we have a circle. Okay, equation of a circle. Now you need to find out the most probable point. That means every point on the circle should be the most probable point, but you will have a minimum beta so that your convergence should achieve. Get it? That is main goal of this algorithm, to find out the minimum distance of the beta so that we can get the most probable value of beta. Okay. Right. Now let's solve this problem. One limit state equation is given and which follows normal distribution. Both the limit state as follows normal distribution. Calculate the value of the direction cosine of the first random variable. कैसे करोगे? How you can going to solve it? How you can going to solve it? बोलो. So first you need to convert it into standard normal space. You have mu and sigma. You just convert it into standard normal space. So you have the value of gz. Yes or no? Now to find out the direction cosines, what you need to do? You need to differentiate that gz with respect to z1. You will get this is at 20 and d of z2 gz by z2, you will get as -6. So once you get the direction, the derivatives of the limit state function, you can find out the Euclidean norm. And once you have Euclidean norm, what will be the value of alpha? It's nothing but minus dg by dz1 divided by norm of g. Solve it and tell me if you are getting the value or not, or is the problem is clear or not. Abdul, clear? Robert?
Yeah, it's clear. I'm getting the values. This seems a bit different. It's just because it's following a normal distribution.
Yeah, these are following normal distributions. These are following normal
Okay,
distributions. That's why. If that not follows normal
okay.
distribution, then we first need to convert it into normal distribution or equivalent normal distributions. Then we need
Uh,
to solve the
uh,
rest of the problem.
I get it. I get it.
Okay, these all problems we are today solving, it's are uncorrelated and all are normal. All are normal. If these are non-normal, then we need to first convert it into normal. Then only we can solve using this process or equivalent normal. Okay.
All right. Okay. Okay.
Okay. So now this is a Newton-Raphson technique. You know that Newton-Raphson technique. I will not spend time in that. Now again, we have another problem. Like we have three random variables, two random variables x1 and x2 that follows that normal distributions, and the final value of reliability index beta is given. The corresponding direction cosines are given. Find out the design point in given space. So tell me how you can find it out. Your x1 and x2, these are two random variables, and these properties are given. Like x1 follows normal of 100, 3, and x2 follows your 75, 4. Now your final value of beta. This is the final value of beta, and these are the final values of direction cosines. Now calculate the design points in the given space. That means you need to first find out the z1 and z2. Then you need to convert z1 into x1 and z2 into x2. That is only your task. Can you do it?
Yeah.
Yeah. That's
I
it.
was I was saying whether it's possible to refresh our minds on the Newton Raphson. Just a refresher.
What for this problem?
I'm saying the Newton Raphson. If you could just refresh our minds on that question, the one before this.
Okay, 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 okay. Okay. Is it visible to you?
Yes, it is.
Yeah. So you can easily solve this problem. Just everything is given. You just need to convert your z into x space. You can check
Yeah,
the
this one
values.
is okay.
Yeah. Okay.
Yeah, this one is fine.
Yeah. Okay. So one more problems we will solve here. Then we will go to our algorithm in MATLAB. So here, like correlated case are there, but we haven't talked about the correlated case today. But for now, just for one problem, we will discuss about this thing. So if correlations are there, like correlation between your x1 and x2 is given. So first, what you need to do, you need to uncorrelate that things. That means you just need to perform the eigen operations. So precisely here the eigen operation is done. Cy, that means B transpose Cx into V. Okay, and V, the eigenvector matrix is already given. So it's nothing but the eigen operation. That means you are decoupling that covariance matrix from the coupled form. Okay, you just need to perform this metric operation. You will find this value, and once you have find this value, these are nothing but the covariance of x. This is nothing but the covariance of x2, and once you have covariance of x1 and x2, you can easily find it out the sigma 1 and sigma 2 values. Clear? Okay, now let's quickly go to our main problem, like how we can code it and solve it. That is our main task, and that should be our main task to solve it. So just stick to that problem. Like we have solved this problem, uh, cantilever beam problem, and we have seen that uh, that Rackwitz algorithm, how to solve it. Okay, so let's quickly go to the algorithm first. Now tell me, you got the algorithm, how this algorithm works and what this algorithm actually do? Yes or no? First you need to understand it, otherwise you cannot solve it.
Yes.
Okay, so let's go to the algorithm and we will solve some problems. So here is the algorithm. And one more thing, we have already seen that the lack of invariance problem here, if we use that Rackwitz algorithm to solve here, the values are, the estimation value here. The second problem I have already solved here, and I have checked that the lack of invariance have already been addressed. Look at this, the beta value, the final estimate of beta will be same for two cases, and the final estimation of that PF will also be same for these two cases. So we don't need to worry about the lack of invariance problem while we are using that Rackwitz algorithm to solve the problem. Okay, so let's go to that MATLAB and code it. First we will go through that problem. So okay, yeah, Naveen. Okay, is my screen visible?
Yes.
Yeah. Okay. So just recall the algorithm. So here, what we are doing here, just we will see. So here, first we will, solve the Rackwitz algorithm using the root finding techniques, and then we will go for the Newton-Raphson technique. That Newton-Raphson technique is another kind of techniques like using root finding technique, we will have some convergence issues. We will see. Then we will directly go to that Newton-Raphson technique, where the root findings, that problem with that convergence will not arise. Okay. So first, let make a function file. So here, like I have made one function file for this form using Rackwitz algorithm. So here the function file says, or what that function file, the input for the function file is, you need to provide your limit state function. You need to like here I am calling it with qn question number. I will tell what that question number suggests here. X, the random variable we have, and the mu x for the random variable, and sigma x for the random variable. Initial value of beta. Now index, like how many random variables are there. For this I have to do some indexation and all these things. And this is like solve switch. If you want to solve it using B root or Newton-Raphson technique, there are switches to solve it. Okay, now this algorithm start like that. Like you need to first define that number of random variable you have in your limit state. So number of variable is length of x, whatever x you are giving the input. Now here number of iteration, like maximum iteration up to which you want to go for. Here I have put like 50 iterations, like no questions will exceed that 50 number of iterations. So 50 is more, you can put it like 10, 12 or 15 where you want to stop. So I suggest like put number of iteration, that is the maximum number of iteration your code will go for. And tolerance, I have given the tolerance as 0.001. What is that tolerance? For the stopping criteria, when your finding of beta will stop. So first here like symbolic variables. In the term of symbolic variables, I have stored that things. So first put it like in a symbolic variable terms, and then I have stored that z values. Like, okay, I need to I need my limit state function in standard normal space. So in terms of z variables. Okay. Now, if correlation are there, so we haven't talked about correlation. So if correlation are there, it will check if there is any correlation. So it will do the eigen operation in that three lines. If not, then directly it will, skip that thing or skip that step. Now, I have that cx value. Now I have the mu value. Now, easily what I can do here is I can find out the value in the terms of z domain. Look here, x1 is equals to v into sigma y plus mu y divided by sigma. That same term is here. Now, Robert, you are saying that if we have non-normal variables, so we need to convert it first equinormal. So we haven't talked about equinormal today. We will just talk on the next class how to solve it equinormal function. So there are one more function which actually tells about how to convert the non-normal variables into normal variables. So this part here doing the convergence from non-normal to normal. So you can, for now you can skip it, like, okay, we all have the normal variables for now, so we don't need to convert it. For ultimately we need to so convert it for, if you want to make some generalized code, so there can be non-normal correlation will be there. So you need to make one code so that it can handle or it can process all kind of random variables. So first what we need to do, we need to convert the limit state into gz. So here the limit state we have converted into like v into sigma z v. That means after getting the uncorrelated form plus mu into equation 1. So if you saw that equation, you can see it. Now here I am calling the limit state function using this. Like, for the limit state function, what I have done, I have created one separate file gsc. Now if I open that gsc, one second, you will get that I just put the limit state here. Okay, here. So you can see all kind of limit state you can put it here. So if I put the limit state here, like I need to find out one problem, like the beam problem. So beam problem, what was the limit state? There was two random variables x1 and x2 minus 2 into x3. So our limit state g of x is equals to x1 x2 minus x3. So I put that limit state in a separate file so that I can call it when we need it. So here we can see that in that step, when we convert that limit state into gz, I am calling that gsc, giving the input like question number and xz, like we will see when we will call a function. Now once we have the gz, here we have the gz, what we need to do, we need to find out the differential of gz. Okay, so here the differential of gz with respect to the number of variables are done. Okay, now once we have the differentiation of the random variables, we need to find out the direction cosines, and direction cosines are nothing but dgz by equidium norm of dz. We have already seen the formula right now. Now once we have the alpha, we can find out the zeta. That means z is nothing but your alpha times the initial beta. That is nothing but the initial beta you have considered. Now once we have that two value, you can formulate your gz. Substitute gz, z and z2, you can get that equation whatever we have solved here. Now once we have that gz in the form of beta and alpha, we can solve this gz using root finding technique like b root, or we can find out the Newton-Raphson technique. Now for the Newton-Raphson technique, I have created another function file to solve it. We will see, but today we haven't solved using the Newton-Raphson technique. So we will stick to just root finding technique. That will work good for this case. Now once we have the roots, so we will get the beta. Once we have get beta, we can find out the alphas, and we can check the difference of this beta, final beta and initial beta, is it within the tolerance limit. It will stop here, it will break, otherwise it will, this loop will continue until that tolerance will achieve. Okay, once that tolerance will achieve, we can calculate the value of beta, that final beta, and once the beta is achieved, we can find out that PF, like probability of failure, will be nothing but like phi inverse of beta. And once we have found out beta and that alpha points, we can calculate the XF points. That means the final design points in X domain. And that will be nothing but you just need to convert it from standard normal space to normal space. Clear? So this is a simple short function file for solving that Rackwitz algorithm. So let's quickly solve one problem, then only this thing will get clear. So what was the problem for our first problem, that cantilever problem? So let's quickly revisit the cantilever problem. What was the values for it, so that we can put these values here. Like cantilever problem, look at this, we have three random variables and they are normal and uncorrelated, and the mu and sigma values are provided. Just remember these values because we need these values to put there. And what was our limit state here? Limit state is nothing but x1 x2 minus 2, I put the value of L here is equals to 2 into x3. Now let's go to the algorithm. So here I am, this is the main file from where I am calling this all functions. So here I am giving a question number, like you can put all other questions and you can alter the switch and call one by one to check whether your estimations are getting or not. So first I am getting, okay, this is my Q1. So Q1 is related to your GSC. That means that Q1 will take whatever the limit state you are providing in the GSC function file. So GSC function file already I have provided. Okay, this is my limit state function. That means when I am giving that, okay, Qn is 1, it will take the limit state this. Why? If put all 3, 4, 5, 6 limit state, like here I am solving like 12 problems in one limit state function. So you can call it with respect to your question number and corresponding values of random variables. So here we have only three random variables. I just define the limit state here. Now what I need to do, I need to define the covariance matrix for this. So here I have defined the covariance matrix. We have three random variables and they are uncorrelated. So that will be nothing but this is sigma 1 square, this is your sigma 2 square, and this is your sigma 3 square. Already these values are given. Now mu, similarly you need to define the values of mean here. So mu I have defined here, like for the first variable the mean is this, for the second variable the mean is this, for the third variable the mean is this. Already these are given here. If you go here, like you can find out the mean values of these three random variables and the standard deviation. If you know the standard deviation, you can find out the correlate, that means covariance matrix. Now once we have done, we need to provide the initial value of beta. Like here I am providing the initial value of beta 3, and this index, like this index deal with how many random variables are there. Like I need here, because while doing the that function file, I need to tell that function that how many random variables are there. So here, like I have three random variables, so I need to define that, okay, 1 1 1 3 is there. This here x 1 2 3. Now this index, actually this index is related to, sorry, this index is related to normal and equinormal random variable. So I will tell in a minute. Here for here 1 1 1 means all are normal random variable. That means you don't need to convert it into equinormal or another random variables. Okay, now here if we solve that using Newton-Raphson technique, that true switch will give. And here look, I am calling the form function file giving question number x, that means the number of random variables. We have three number of random variables, and this index actually deals with the equinorm thing. Here if you see, like when we need to convert it into equinormal space, we need to know about which random variable is normal and which random variable is non-normal. So here for our case all the variables are normal. That's why the index are 1 1 1 for this function file. You can you can control it in another way also. And now ultimately I am calling the form file using question number x, mu x, corresponding that covariance matrix, initial beta, and index. That index is for, is it a normal or is it different kind of variables. So equinormal things will does, and solve in our switch is like Newton-Raphson se solve karega, or it will solve through p root. So we can solve it using two process also, like we can stop the Newton-Raphson here and we can solve b root. That two will give the same results. Okay, so quickly if we go through this function file, these are the inputs like question number, x, mu, sigma, initial beta, index, and which method you are want to solving. And what are the output for this function file? It will give your final beta, final PF, and the final design points in X domain. And similarly, that xd, like here xd, like xfs are there. That means one value of design points you will get. So either xf or xd you can control it. Like for this checking I will just put that xd. That means I can get all the iterations for this. You can skip this also, no problem. So now if I want to call this function and solve this equation, so what we will get, just let me check. So just call it. Yeah, it has already solved. Now let's look for the solutions here. So initially it has started from 3, then we get 2.26. Like if we go to that values of table, so we have that clear understanding. Like, yeah, so it's quite difficult to show two at a time. Like just think, like first iteration 3 start, then we get 2.26 and corresponding alpha and zeta and all these things, and from third iteration we will get 2.25, and exactly your that code will calculate this. So second iteration we will get this 2.2689. We'll get this alphas. Look at the alphas, whatever you have calculated you are getting that, and corresponding zi. Then again based on this zi, it have calculated beta and corresponding alphas. Again for this alphas you have calculated z, and again for this z's it has calculated the xf values. Finally it has converts to 2.2576, and for this our final value of z star is this 1.15, 0.66, and 1.55, and corresponding that xf values. That means we just convert it into here and we will get this. So it's a very simple algorithm. You can solve any problem of first order reliability method using this. Like if we want to solve another problem and see or check whatever we are getting the convergence or not, so we can check in a minute. So tell me, is the algorithm clear to you? You need to check it, like you need to go through the algorithm step by step and you need to play with it. I will upload the function file along with the problem. Okay, so do you have problems? Like, yeah, you will have problems, but you need to solve it first. Yeah, Bob.
Yeah, for me, I'm totally confused with this MATLAB because I'm not used to it. So I'm only listening to what you are saying.
Okay, okay, okay. Actually, I have, that's solved the issue. I will share today. Okay, you need to practice it. Otherwise, like these iterations we have solved using MATLAB is just 2 minutes to solve, 2 seconds to solve it. But if we want to solve it through pen and paper, it will take hell lot of time. Like look at this, all the values it has printed whatever you want to get, and this is the your final pf and this is your final beta. You will get all these things from the code. But Robert, I think you have understand the algorithm how it works. Yes or no? You have the visualization. Okay, this way this algorithm of Rackwitz-Fissler will work. Yes or no? How we are solving the process, how we are getting the design points. Is it clear?
Yeah.
Yeah. Also we will, on the next class we will just spend time on that coding. Okay, we will do step by step so that we can solve this simultaneously. Now if we again solve another problem, like let's say this problem, I have added few more problems here. Here this problem, here we have 1 2 3 4 random variables, and if we want to solve it, it will take like 5 iterations to solve it. 5 iterations to solve it. Even we can go more up to this. If you want to solve it like here using MATLAB or using that Rackwitz-Fissler algorithm, you can solve within you know uh, within 2 3 minutes, and within 2 3 minutes you can solve it. Like we can solve another problems. Like here I have added few more problems here. Now tell me which one you want to solve it, which problem you want to solve it. Like here we have this problem. Let's go to, we can solve this circle problem. Let's solve this circle problem. Okay. So we have, I think I have added the circle problem here. So GSC, look for circle problem. Where is the circle problem? Here. I have defined the circle problem, question number 8. So let's call for question number 8 and check whether we are getting the same values or not. So question number 5. Question number 5, and just run the algorithm. Yeah, I think that is not the question number 5. That is the different question. One sec. Any problem using that function file and using this problem, you can solve any problem, any kind of problem. How much iteration? Question number 8. Sorry, not question number 5. It's 8. Question number 8. If I want to solve that problem, so let's see what the algorithm gives us. Yeah. So it's given the final beta 1.98 and the corresponding probability of failure. Beta is equals to 1.97 and corresponding probability of failure. And if you see, we have this 1.97 and corresponding probability of failure as 0.023. Okay, so let's quickly go through this algorithm once again. Like here we can solve any kind of problem. Like if we have changed the limit state, like we have that thing, uh, lack of inference problem. So here we have two limit state. Like see here we have two limit states. First I have question number 11. Just look at this question number 11. X1 x2 minus x3, the first case we have considered, and the question number 12, 1 minus, that means question number 11 is c minus d format, and question number 12 is 1 minus c minus d problem. That your cantilever beam problem here, the cantilever beam problem where we have seen the lack of invariance problem. Okay, so first case, if we solve the first case, that was the first case, we already solved it using pen and paper and using MATLAB also. Now if we solve the second case, so the question is, are we getting the same values or not? Let's say, so question number 11 and 12 we need to solve it. So question number 11, so let's see, question number 11 we have put all these values or not. Yes, question number 11. Okay, 2.5 into 10 to the power 4. Yes, 6.6 into 10 to the power 10 and 10 to 15. Yeah, all values are same, all values are same. Let's run question number 11 first. So what we will get? Yeah, we are getting the final value of beta is equals to 2.258. Yes, and these are the design points, and this precisely this is last column is the final design point. That means 2.258 if we consider the limit state function as c minus d, and the probability of failure comes as 0.1198. Here we can see it, 1198 and 2.557. Like if you round off, 2.58 will come. Now if we convert it into 1 minus d by c, you have seen that lack of invariance will occur if we solve using MBFOSM. Now let's solve using this Rackwitz algorithm. So question number 12, if we change it to question number 12, that means in question number 12, what we have done here is we just change the limit state into 1 minus d by c. Here you can see it here, 1 minus d by c. So now let's solve it. Yes, we are getting the same values. Although we have, changed the format of the limit state, still we are getting the same values. That means the probability of failure for the final estimation, if we change the limit state function, we will get the same values. Clear? So this algorithm is efficient, but one more thing I want to highlight here, like instead of root finding techniques, if we use the Newton Raphson technique to find out the roots, so it will give us better convergence. That means in some problems where the limit state, the non-linearity of the limit state will increase, then the root finding technique will fail sometime to converge. Clear? So we can solve different problems. Whatever the problems are here in the PPT, we can solve it. Like this problem, whatever we have solved it. Now this problem, look at this. We have 4 random variables. This is the limit state function. So our goal is to find out the final points. How we can find out? Let's solve this problem. So if we want to solve this problem, first we know what we need to define. We need to define the limit state here. So I think I have defined the limit state here. Question number 9, you can see the limit state is defined. Square root of 2 square root of this 200 into x2, 5 into this. Just this 200 into x2 and the rest of the thing 90 into x3 and 5.4 into this. And corresponding that mu and sigma values, just carefully get it from here and put it there. So this is nothing but we are looking for question number 9. So question number 9, I have put all these values, I think. Yes, question number 9, look, for these 4 random variables, I have put all these values here. Now you just need to solve it. Like, look at this here. The indexes are given like 1 3 1 3. That means that thing I will talk on the next class, how to convert it using that indexing properties. So for the time being, if we consider that all are normal random variable 1 and 1 means all are random normal variable, 2 log normal, 3 different kind of things are there. If you go to the equinorm function, you will find it out. So now if you solve it, it will give us the values, but it will take some more time to iterate. 2.23 and it will give it that. No, we need to change the question number first so that we will get the value. It will run the question number 12, so just put it to question number 9 and run it. Yeah, we will get the final values 2.9 and 0.0018 as the final estimation of beta and these things. So we can see, yeah, like this. So here the random variables are, I think I have changed some questions for there. Here x1, x2, x3, whereas the standard normal variate. Okay, no problem. So if you solve it by this way, you can find out the beta. You just check this problem. Okay, I think the values are given here is okay. 2.29, 2.29 is coming, and in PPT the value is given as 3.2. I think some values, like that problem was for normal and standard normals case, so that's why the value is coming different. Okay, and this case is different, so we need to carefully put the values. I think that values are not given, like you need to find it out the mean values and standard normal values and put it respectively and solve the problem. So here I think we have another problem, like we have, yeah, that double reinforced beam section. You can solve this problem too using that. I think I have also added this thing. GSC form, if you look for GSC, you will find out that problem too. Here, question number 7. Question number 7, that double reinforced beam is there. So if you run the question number 7, you will find the answers. So if the values are properly given here, like I have consecutively checking the things, so maybe I have changed some values, but most of the cases these are given 4.42. Let me check once again. Then okay, these are different problems. Like I think the normal random variables I have casted it for different problems. That's why problem number 7, problem number 7, where is the problem number 7? Yeah, actually the for the problem number 7, 111 is given. Okay, I have changed this problem to another problem. This is not that WN plus problem. What you need to do, like if you want to solve this problem, what is your WN plus beam problem? Yeah. So what you need to do, first you need to define that limit state function. You put all these values here in the limit state equation and you call that form function. You will get the value. So question number 7, again we will run it. Yeah, you just check these questions. Okay, whatever these values are given is okay or not. But I have checked these 4 questions, like for the circle problem, for the beam problem, for the beam problem, and this question number 7. I think this question number 7 will also give the same result, but the values you just need to put it here. You just need to go through it and check it. I will provide the code and the function file. You just need to play with it. Okay, whatever values you are getting is okay or not. So I think it will give the same result. Question number 7. So just check the GSC. Okay, I might miss to put a few values. Just check it and corresponding values we will get it. Yeah, it's giving 4.42. So just check it. Either these values is correct here, these values is not given properly, or I will check the code and I will give the proper values. Okay, no issue. So let's quickly go through the algorithm once again. What that form new thing does. What it does, first it will check if the correlation are there or not. If there is no correlation, so it will simply bypass this step. If there is correlation, it will uncorrelate first. Now once it will uncorrelate, then what we need to do, it will check if all the random variables are normal or non-normal. If all the variables are normal, it will not convert into equinormal space, and if not, then one function file I have generated for different convergence. I will talk on the next class. Then what it does, once these things are done, we formulate the gz into standard normal space. Once we have gz, we need to differentiate the gz to get alphas. So these are the differentiations. Now here the differentiations are done with respect to diff command. You can use the central differential method. I suggest you go for central differential method because the convergence issue will not be there. Now once the differentiations are done, we can find out the direction cosines. Direction cosines are nothing but minus of norm of that z divided by equidistant norm of your dz. The two, that means your equidistant norm. Now once we get that values, we can find out easily the z2 values, and once we have found out the z2 values, we can easily calculate the gz value. That means the final equation in terms of beta. Once we have that final equation of beta, we can find out the root of beta either using b root command or using Newton-Raphson root finding techniques. Now once we have found out the beta, we can calculate the alphas and check whether the initial beta value and the final beta value, whatever we are getting, that means the I beta and I plus 1 beta, the tolerance should be within whatever tolerance you have set as a limit. Now once if we achieve the tolerance, the loop will break here. Otherwise it will continue until it will converge to that, or it will achieve this level of convergence. Now once we have get the convergence, we can have the final beta. If we have the final beta, we can get the PF, probability of failure, and we can convert that Z. Once we have found the beta, we can found the Z. Z is nothing but, alpha into beta. And once we have find out the alpha and beta, we can calculate the X term in X domain, and we can find out the final values of design points. So this how this Rackwitz algorithm works. But here the Rackwitz algorithm has some limitations, like roots. We are finding the roots using root finding command, and we incorporate actually the Newton-Raphson technique into that Rackwitz algorithm. That will be more efficient. Like I have that function file for it, how to solve using Newton-Raphson technique. So that is actually helpful for you. NR form, actually this is form M2. So we will solve this, like this is more precise form of code. Okay, and here in the metric notation, all kind of problem you can achieve it, the convergence. So this function file form M2 we will discuss on the next class, line by line how. Before that, we need to understand that convergence from non-normal to normal space, and nothing but if correlation are there, you need to put some loops or put some checks where that if there are correlation first, that correlate to uncorrelated things will do, and then rest of the things will solve. Okay, so like you need to first go through it and solve one or two problems. Like the problems, two or three problems I will upload, and corresponding MATLAB files which are related to that corresponding problem, and you just practice it until the next class, and tell me if you have any problem, just share with me on the next class. Okay, so tell me if you have, hi, where we can get the solved example PPT.
Please, can you solve one question with the Newton-Raphson technique? Just one question.
One question, one full
Yes.
question. Yes, I have actually solved this one full question using Newton-Raphson technique here, and that is solved using pen and paper. This already been solved, na, Robert? Just go through it. This is
Okay. Okay.
step by step. Then we have solved this problem also using Newton-Raphson technique. Oh, sorry,
All right.
you are calling the Newton-Raphson technique. Okay, problem
Yes.
regarding Newton-Raphson technique. Okay. What kind of, like root optimization problem?
Yeah. Just one question so that
Like what
you can
Newton-Raphson
have.
does? Okay, okay. Let's go to this problem. Okay, say I have added one problem here, Newton-Raphson technique. Like
Okay. Thank
Newton-Raphson,
you.
yeah, like Newton-Raphson technique. Can I get this discussion and solved example for our reference? Yeah, man. You are new, I think. We already upload all the recording videos and the corresponding sessions you will get from the public seat, I think. Abdul, you are getting that all the assignments, codes, and the PPTs, right? Abdul? Okay, you will get it from that code. Today already we will upload it, and on every session, after every session, I upload that PPT along with the solved problems and along with the MATLAB script. So, Balaram, right? You can unmute yourself. Yeah, you can unmute yourself. I can see you actually.
Hello.
Yeah, yeah.
Okay. Actually, I'm new today, so I was not knowing.
So, are you registered to that NPTEL course?
Yeah. I have registered in the NPTEL course.
Yeah, so that they will share some, Google Sheet form where you
Okay.
can get the video link for this recording session, as well as the materials, as well as the
Okay.
MATLAB codes. Actually
Okay.
they are uploaded in the different folder, and they share
Okay.
some spreadsheets along with feedback form. So
Okay.
you will
Okay.
get from there. And I generally,
Okay.
after every class, I upload these things so that you can practice it and you can develop some codes if you need additionally. Like I upload this PPT along with that MATLAB function file, whatever we have discussed today. Okay, you will get it from here.
Okay, okay,
Okay,
okay. Thank you.
okay. So from where you are from? Okay, no issue. Robert, can you get it that like how we can solve using Newton-Raphson technique? It's like finding the roots from the first iteration. This is the format for the Newton-Raphson technique. This is actually the format for the Newton-Raphson technique. Now in the first iteration, you just need to differentiate with respect to this, so you will get the value. For the second iteration, likewise, it's a very simple technique. You just go through it, you can easily understand. Okay. So actually on the next class, we incorporate from into Newton-Raphson technique. Actually, these formulas, we will work with that. And that will give us the optimum code for the Rackwitz algorithm. This will actually give us the code for Rackwitz algorithm. Okay. And for the Newton-Raphson technique, you can go through any kind of standard books where you can find out for the first iteration, second iteration, and third iteration. Like this problem, you can easily find it out. The roots, where?
Yes, because you have a couple of them in the assignment. So
Yeah, I think one. This this you can easily get it. Like
yes,
you have this function, you can differentiate with respect to this. Just for the
yes,
first,
sure.
this is the expansion form of the Newton-Raphson technique. So for 1, you can put n equals to 0. For 2 is equals to put equals to 2. Just you need to differentiate these two functions and get the values one by one.
Okay.
It's finding the root with
Mm,
respect to differentiation, just like that. So get my point? This is actually the expansion form. So if you put n equals to 0, it will get the first iteration like x1. So x1 will be
yeah, yeah,
x0, fn0 and f dash 0. So you have got these values from here and the initial values of
yeah.
x are given here. So just the iteration, derivatives and iteration, that's all. Okay.
Okay.
Okay. So do you have any questions or we can, conclude this session and we can meet again on the next class. So next class we will spend time actually solving the problems. Today we haven't solved much problem related to this first order reliability method. We have just solved problem using pen and paper. But actually on the next class we will solve problems step by step on MATLAB. And that is very important for correlated uncorrelated case, how to solve it, how to make the function file for it. Like if I go directly to the function file today, all of the function files, it will be very problematic. So what I will do, I will upload only one problem, like this first problem. That means this cantilever beam problem. You can solve it by your hand already, now if you run this, you will get the values also corresponding to that form file. So all the values will be there, like 2.258, the final value. We have calculated for 2.258, I think, yes, 2.258, 2.2577, and the final value of probability of failure 0.0199, and we are getting the same values. And if you change the limit state, you will get the same values we just have seen. So I will upload these things today, and on the next class we actually, I want to get things clear. I Today you will get some concept about that Rackwitz algorithm, how we can find out that MPP using that direction cosines. Actually we will code it. Just go through it. Next class you ask question, okay, from where you are getting this, how to solve this code. Like this function file is very simple and easy. Only you need to provide this input like this random variable mx, qx, and cx, the variables and the limit state function. You will get beta, probability of failure, and the final design values. Okay, so how we can incorporate this algorithm to our real life problem? We can see many of the problems like here, that W reinforced beam. If we have the W reinforced beam, what should be the most design points or probable points for aim, XU, and FSC? So this all kind of question can be solved using these techniques. Okay. So so do you have any doubts or questions? You can ask me or you can conclude here. Anything. And yeah, Bob, I will share it today. Okay.
Okay.
Only
Okay.
to your
So
student you can get access. Yeah, tell me.
I was trying to find out if any of the students can help me get the student version so that before you help me in the finally with the
Yeah,
MATLAB because I have.
just go to the MATLAB official site. You will find out the procedure how to install the student person, or you just search the internet. You will get it.
So it's part of the course
Yeah,
information.
yeah, yeah. For this course, I think you need to mail to NPTEL to get access to that MATLAB.
Okay.
Okay,
Okay.
and
So
then I have figured it out with respect to that. Whatever I have told you, I just share it with you. Just go through
okay,
that.
okay, okay. That's fine.
Yeah,
All right. All right. That's good. All right. I'll
yeah.
be expecting it. Thank you very much.
Yeah. So there's are some readme files. You just go through it and you can figure it out easily how you can do it all these things. Okay.
All right. I really need it.
Anyone like Abdul, you have any doubt or any questions? You can ask me. Or anyone, or we can conclude here. Okay. So we will meet on the next class. Thank you.
Thank you very much.